Okay, so now let's talk about confidence regions and confidence intervals, simultaneous confidence intervals. Confidence regions come right out of the results we've seen for the t-squared test. The t-squared statistic, if you recall, write it down back up here. We have a random sample, x1 through xn. These are independent and identically distributed from, we're going to say for now, multivariate normal. So p-variate, multivariate normal with mean vector mu and covariance matrix capital sigma. For testing, if we wanted to test, say, the null hypothesis that mu equals some specified value, we have learned to use the t-squared statistic. T-squared statistic is statistical distance between sample mean and the null hypothesized mean. So statistical distance looks like sample mean minus null hypothesized mean transpose, and then over here I'm going to have, again, x bar minus mu0. And what needs to go in the middle is the inverse of the covariance matrix of x bar. We know that the covariance matrix of x bar is capital sigma divided by n. The mean of a, or the variance of a mean is population variance divided by sample size. So in this case, I'm going to put my estimate of sigma inverse right here. And here's my n. That's the t-squared statistic. Statistical distance between x bar and the hypothesized mean. It's this thing right here. And what we've seen, if you have multivariate normal data, then the distribution of this thing is this scaled f that we saw in an earlier slide. So this is a random variable, scalar random variable, and under the assumption of multivariate normality, it has a scaled f distribution. So if I wanted a region for mu such that I could say the probability that mu is contained inside this interval equals a specified value, I can use this probability result to do that. Specifically, if you want, say, a 100 times 1 minus alpha % confidence region for mu. This is not an interval, it's a region. It's a multidimensional region. If we want a region about which we can say, I'm, say, 95% confident that mu is in there, then we can use this f distributed result. Specifically, we could find the values of mu such that the distance equals this, where this is the appropriate percentile from that f. So if this was the 95th percentile of the f with p and n minus p degrees of freedom, and we multiply it by the appropriate constant, then the probability that this is less than or equal to that equals 0.95. So if we could find the region of values such that this equals that, that will be what we can call a confidence region. Those are the points for which the probability is exactly alpha. So everything inside would be corresponding to 0.95. Let me show you an example. So here is the container data and just 2 of the elements. Remember, these are, we had like 10 containers, and each container we had multiple elements that we had concentrations for. Suppose we only looked at aluminum and iron. The sample mean vector is here. The sample covariance matrix is here. And if we wanted a 95% confidence region for mu, the 2-dimensional mu, what we need is the appropriate number, the appropriate percentile from this F distribution. So in the container data, if we do n minus 1 times p divided by n minus p, that ends up being 18 over 8. And the percentile, or the critical value from the F, I can get it out of R, and the number turns out to be just over 10. So any value for mu that has statistical distance square root of this or even smaller is inside what we're calling a confidence region. All values of mu such that the statistical distance is 3.1674 or smaller is a plausible value for mu at 95% confidence. That's what we think about with confidence intervals and confidence regions. We're asking about plausible values for a scalar parameter, or in this case, a vector parameter. What we get is an actual region. In 2 dimensions, it's an ellipse. For example, mu transpose equal to 0.9, 0.13. If you plug in 0.9, 0.13 into this calculation, we would have x bar right here. Capital S is defined here. If we plugged in this specific choice for mu, you would get a distance, this distance right here, the square root of all that mess inside, comes out to be 1.4887. That is less than 3.1674. So that choice of mu is closer to our observed data than the threshold, which means that that choice of mu is a plausible choice at 95% confidence. A slightly changed value of mu, 0.9 and 0.15, if you work out its distance is bigger than that, so it is not a plausible value at 95% confidence. That's the way you would use a confidence region. It's a region for the entire mean vector. So you can check a particular mean vector by asking, is it inside this region? Let me show you the container data. Container.r would have code for doing this. Let's go ahead and load these in real quick. We could check normality, group-specific mean vectors. Here's 3 elements. Here's all elements. Here's the code from the slides. So I'm going to do a confidence region for only aluminum and iron. P is 2, X bar is the column means, and capital S is var. Here's what we get when we run that. X bar, 0.8802 and 0.1237. 8802, 1237. And we have capital S, which looks like that. So let's compute a confidence region with these data. I have a function here that will actually draw the region. Let me go ahead and define this real quick. And then down below, we're going to consider a couple of different possible values of mu. Like on the slide, I said, is 0.9 comma 0.13 in the region? It was. And then is 0.9, 0.15 in the region? It was not. Right here, I am computing the distance within which defines the confidence region. So this goes to get the scaled F percentile. Go to the F distribution with P and N minus P degrees of freedom and give me the 1 minus alpha percentile. If I'm doing alpha equal 0.05, see where I defined alpha, somewhere up here. If I'm doing alpha equal 0.05, then this would be the 95th percentile. I need to define alpha somewhere. Let's say alpha is 0.05. That means, 95% confidence corresponds to an alpha, or type 1 error rate of 0.05. So if I compute this quantity right here, I get 10.03. That's that number right there. So I plugged in the appropriate percentile in order to carve out 95% confidence. I computed this number, 10.0327. And then, right, in the next two lines, I'm computing the value of t squared for the two mu choices that we're considering. So the first one, t squared underscore 1, is n times x bar minus the mu first one transpose S inverse x bar minus the same mu. The next line down is the exact same, except we changed the value of mu that we're looking at slightly. Here are the two t squared statistics, 2.22 and 24.56. And so we could ask whether each of those is less than this threshold. The first one is, which means that that choice of mu is close enough to our observed sample mean to be plausible at 95% confidence. This one, however, is not. It's further away than our furthest allowed distance. Okay. Let me see if this function will work for us here. Yeah. Draw dotted ellipse. So based on our little data set, we had an X bar of 0.88, comma 0.1237. So 0.88, 1237. There's the center of my observed data. X bar is right there at that black dot. The 95% confidence region, the set of points that are equal in distance to that threshold based on the F, is the ellipse. So the same basic idea for drawing ellipses applies here. The angles or the directions of the primary directions for this ellipse are eigenvectors of capital S. The lengths of them are functions of the eigenvalues of capital S. The green dot was the first choice of mu that we considered. It's inside the ellipse. The distance, statistical distance to x bar, was less than this maximal distance. The red dot, the second mean we looked at, was not inside the confidence region. So if we want to have some kind of confidence statement about a mean vector, then confidence regions are a possible solution. And confidence regions, when we're dealing with mean vectors, they are just, they come right out of using that t-squared statistic. T-squared is a statistical distance, and if we assume multivariate normality, the t-squared ends up having this F distribution. So those are the key components. If you want a confidence region for a mean vector mu, you compute the t-squared statistic, and you get critical value or limits for the ellipse from an F distribution. All right, so that's a confidence region. In my experience, most people would rather have confidence intervals for each of the individual variables. That it depends on the setting, but sometimes you would want a region for an actual mean vector. Like suppose you're doing quality control of a manufacturing process or something, and you have 5 different variables that measure the quality of the process, and those have to simultaneously be within bounds, reasonable bounds. Then a confidence region makes sense. But next we're going to think about how do we go from a region to individual intervals for our individual variables. The challenge is we have p variables now. So while a confidence interval for any one variable is not hard to do, that's Stats 101 stuff. If we want to have p confidence intervals, we need to be careful about how we construct them, because if, for example, we did a 95% confidence interval for variable 1, and then separately did a 95% confidence interval for variable 2, ... If we did that for all p of our variables, the probability that every one of them contains the truth is not equal to, say, 0.95. If I had p equal 5 variables, and I did a usual univariate style 95% confidence interval for the mean of variable 1, and then I did a usual univariate style 95% confidence interval for variable 2, and 3, and 4, and 5. Overall, I don't have like a 95% simultaneous set of confidence intervals. In particular, it is not true that the probability all of these intervals contain their respective values equals 0.95. That probability is actually lower now. The probability that any one 95% confidence interval will contain the truth is 0.95. So if I do p of them, the probability that they all contain their respective mean is 1 minus alpha, or say 0.95, to the p. If we're talking 95% confidence intervals, and p is equal to 6, then if you went one by one and did univariate style 95% confidence intervals, the joint coverage probability, the probability they all cover their respective means, is only 0.74. When we go multivariate and we do inference on top of inference on top of inference, we are increasing chances of errors. So, how do we fix that? The main fix is if the coverage is too low, we need to make the intervals wider by an appropriate degree. So how can we take usual univariate style confidence intervals and widen them so that they have joint or simultaneous coverage that we want? Okay, so here's the idea. I'm going to skip over this. There's some math that helps us to solve this problem, but I'm trying to go a little lighter on the math this time around. So let me get to the good stuff. Here's the good stuff. The usual univariate style confidence interval would use a t critical value in it. So for, say, variable 1 with a mean of x bar 1 and a sample variance of, call it s squared 1, we would do x bar 1 plus or minus a t critical value times s1 over the square root of n. When we have univariate data, x1, x2, xn, we'll say they are IID from some distribution with mean mu and variance sigma squared. Then a 95% confidence interval for mu would look like x bar plus or minus a t critical value. So this is often written as from the t with n minus 1 degrees of freedom, give me the percentile that puts alpha to the right. Or actually we would do alpha over 2 to the right. T n minus 1 alpha over 2 times we use s over the square root of n. So that looks like estimate the mean, then do plus or minus some cutoff times the SD of the estimate. That's a usual univariate style confidence interval. In order to go to these simultaneous intervals, we need to widen or make this cutoff bigger. So we started here. This is a general way to represent a univariate confidence interval, and we're saying we need this number, this cutoff, to be bigger. It turns out that the magic number, or one magic number we could use, comes from that t-squared distribution. So instead of a t critical value, like this one, if instead you put the square root of a scaled f critical value, if you do that, this number, it turns out, will be bigger than that number, which means these intervals are going to be wider. And in particular, you have this result, which is messy, but let me tell you what it means. We have the probability that the distance, like statistical distance, is less than or equal to this critical value, the probability that that happens for all variables simultaneously is equal to 1 minus alpha. Okay, so this is a little bit subtle math. It is an important point, though. In order, what we're going to get with a simultaneous set of confidence intervals, if we have p variables, we're going to have p intervals, one for each variable, and we're going to say about all those intervals, the probability that the collection of intervals like I collected will be within the right spot is equal to the nominal coverage that I wanted. So I have the ability now, we have the ability to construct individual intervals, one per variable, such that we can say, here's all my intervals, p confidence intervals, and I can tell you that simultaneously they will cover the truth with probability 0.95. That means that 95% of all, if you were to resample data like yours many times, and every time you constructed these p intervals, 95% of all those resampling efforts would result in p intervals that all contain the truth. Whereas a univariate interval, you talk about probability that it covers its one mean. Simultaneous intervals, you talk about probabilities that they all cover simultaneously their means. So in multivariate statistics, simultaneous confidence intervals are really what you want when it comes down to speaking about variables individually. It's a little bit messy, but practically speaking, it's something that you just copy and paste multiple times. Instead of doing this style of interval, all you have to do is replace that t with an appropriate f. Let's look at the container data, and I'll show you the code. This is the same exact setup. We have aluminum and iron only. And we're going to compute 95% simultaneous confidence intervals. The number that we need to put for the cutoff here is the square root of that, is that statistical distance that we computed earlier. Back here, this guy. $10.0327. I plug square root of that in place of a t critical value. So I get intervals 8286, 9318, and another one 0.10 up to 0.14. Let's go back to R and see how these are computed. So here is a simultaneous set of confidence intervals for mu1 and mu2. That result that I showed you is actually even more impressive than I'm making it out to be. In particular, you can construct as many intervals as you want in terms of linear combinations of your means. If you want to look at just mean 1, that's a linear combination. That's like 1, 0 times your mean. If you just want to look at mean 2, that's like 0, 1 times the mean. What if we wanted to look at the difference, mu1 minus mu2? We can pick as many values of linear combinations as we want, and as long as we use this cutoff, we have simultaneous coverage for all A simultaneously. It's kind of magical. So if you can take as many linear combinations of your mean as you want and have separate intervals for every one of them. If you spread them out or scale them according to t-squared style, then you have coverage simultaneously for all of them. Here I'm computing 3 intervals, one for mu1, one for mu2, and one for their difference. There's my interval for mu1, my interval for mu2, and my interval for their difference. I could publish all 3 of those and correctly say they simultaneously cover with probability 0.95. Okay. That's one way to do simultaneous intervals. I'm actually gonna recommend to you a different style. Here's a picture that shows what they look like. The black ellipse is the 95% confidence region we wrote down. Those t-squared intervals, those simultaneous intervals, are actually the shadows of that ellipse. If you drop down to the horizontal line, the endpoints of that ellipse are the intervals we just computed, the interval we computed for mu1. And similarly, if you follow to the left of the ellipse, where it marks out on the vertical axis, corresponds to the interval on the second mean. And let me end with this comment. These are appropriately wide in order to give us simultaneous coverage. In actuality, they're wider than they need to be. So the coverage probability is actually bigger than 95%, for example. They're conservative. They're going a little wider than they have to. So we're going to meet a different style of interval. The red dashed ones are the t-squared simultaneous intervals. We can do a little better, have a little less conservativeness about it if we use an alternative called a Bonferroni interval. You've probably heard of Bonferroni adjustments for multiple testing. It's the same Bonferroni, same basic idea. But we're going to be able to have simultaneous intervals for all p of our variables. And notice that the blue ones are narrower than the red ones. So they're more precise. In order to do the Bonferroni approach, here's the way you would do it. You would, for one variable, you do its mean plus or minus a t cutoff, but this is a little bit different from the original t cutoff we saw. A univariate t cutoff would usually be t n minus 1 alpha over 2. But here I have alpha over 2p. I'm dividing by, I'm spreading out the error among p variables because I want p separate confidence intervals. This is exactly like the univariate t-based confidence interval, except for this little factor down in the bottom. Okay. So that's basically it for topic 5. Topic 6 we'll go through pretty quickly next time. It's the same basic stuff, except now we're going to talk about, instead of just one mean vector, we're going to talk about 2 mean vectors, and then 3 mean vectors. So by the end of the week, we'll know how to do inference on mean vectors generally, including multivariate ANOVA. Okay, see you Wednesday. All right, let's see. We are going to wrap up multivariate inference on a mean. Inference on a multivariate mean. Topic 5 is a single mean vector. So we've met the Hotelling's t-squared test. If you want to test whether a mean vector equals a specific value, you can compute this statistic, which is like a squared t statistic, but it's a multivariate version. And then we have a known sampling distribution for that statistic. So I can get a p-value using these results. What else have we seen? Confidence regions, and then we started talking about simultaneous confidence intervals. remember that a confidence region, like here for the container data, I think, 2 elements only, a bivariate data set. We took our n by 2 matrix of numbers, and we were able to compute this ellipse. The way that we computed it, remember, comes from that statistic that we computed, the t-squared statistic. Because we know the distribution of this t-squared statistic, it has that distribution. That means, actually what we need is, because we're dealing with statistic values that are computed this way, and this statistic is a quadratic form. It's X transpose a weighting matrix, positive definite, times X, quadratic form. And we've seen earlier how to work with a quadratic form to get the ellipse that describes its pattern. Namely, get the eigenvalues and eigenvectors of that capital S. Then this ellipse right here is primary axis is first eigenvector of capital S, secondary axis is second eigenvector, and the half lengths are proportional to the eigenvalues. The actual length, where we could make that ellipse be however big or small as we want, all we do is expand about those eigenvectors. The way we chose this particular distance from x bar to draw the ellipse is using this relationship. We know the distribution of this thing is a scaled f. So if we go and get the f critical value, or the f percentile, that puts 1 minus alpha to the right of it, then that will define an inner region for which there's 95% probability. If I get the upper alpha percentile, like for a 95% confidence interval, if I get the 95th percentile of this distribution and multiply it by the appropriate constants, that's the constant distance that we want to allow for. So once we've specified, I want all the points that are that distance, constant distance from x bar here, we get eigenvalues, eigenvectors of capital S. We center it at x bar, the ellipse. We have the axes, and now we have half lengths. The half lengths of the ellipse were determined based on what confidence level did you want. If you want to increase your confidence level, that ellipse is going to grow. You have to get less precise in order to increase your confidence. If you wanted to make it more precise, the ellipse tighter around x bar, you would have to decrease your confidence. There were 2 points included, 2 separate possible values of mu. And the way we would ask, is it a plausible value, is to ask, is it in the ellipse? To compute that, you compute the statistical distance between that mu and x bar. You'll find that it's less than that scaled f percentile. Confidence region is a joint statement. I believe that the vector mu is contained in this region. But we also will usually want individual intervals for each of the variables. In that 2-dimensional case, that would mean I want a confidence interval for the first variable and a confidence interval for the second variable. The challenge in doing that is that if you construct 2 95% confidence intervals, the probability any one 95% confidence interval covers its truth is 0.95. So then the probability that 2 intervals that you construct that way both contain their truth is 0.95 squared, smaller than 0.95. So if we did usual univariate T-style confidence intervals, 1 per variable, the simultaneous coverage for all of them at the same time is not that nominal value anymore. Yes? So question was, is there any difference, say, between a confidence interval and just an MLE? MLE, maximum likelihood estimator, is an estimator. In a multivariate case, it would be a mean vector. In a univariate case, it might just be a mean scalar, single number. Based on a sample of 100 observations, we could compute a sample mean, x bar. That's the MLE. So suppose I have 100 observations. I compute x bar equal 4.1. That's my MLE. That's a good estimate of the truth. But that one estimate by itself is of limited value because you don't know whether it's 4.1 plus or minus 0.1 or 4.1 plus or minus 2. So that MLE, the 4.1, you would call that a point estimate. It's a single estimate, which is valuable but not probably valuable enough in practice because we want that plus or minus. We want a confidence level for it. MLEs give us the estimates. The mathematics of MLEs also allows us to get standard deviations of the estimate and know sampling distributions of the estimate. But the MLE itself is just an estimate. The maximum likelihood, like total machinery, does the whole procedure. Gives you an estimate, gives you a sampling distribution, and a standard deviation, so you can do everything. But just an estimate it lacks because you don't have that plus or minus. Is it 4.1 plus 0.1, plus or minus 0.1, or is it 4.1 plus or minus 2?
I guess my question is there more value in that because it doesn't use an assumed distribution? Like this is using an assumed distribution, and then the mean doesn't necessarily use an assumed distribution.
So an MLE, maximum likelihood is a parametric approach because in order to compute what we call the likelihood, we had to specify a distribution. For example, let's think just univariate case. Suppose we have n observations, a random sample. So these are independent and identically distributed numbers from some distribution, call it f, that has parameters theta. For example, we could say f theta is the normal distribution with mean mu and maybe a fixed known variance. Maybe it's a single parameter. Then the likelihood, a function of the parameters, is defined as the product of the PDFs evaluated at each xi. And then the maximum likelihood estimator, theta hat, is the value of theta that maximizes the likelihood. In order to get an MLE, then, we had to specify a distribution. That f theta is an actual distribution, normal, binomial, gamma, or something. Maximum likelihood is a parametric approach. So that's not ideal necessarily, because it's a little scary to have to make assumptions about distributions. One moment, yes?
What do you mean by parametric approach?
I mean, by parametric, I mean we are specifying for our data that they came from a distribution that I'm going to write the formula for. For example, if f theta is normal, then e.g. if x is normal with mean mu variance sigma squared, then I know the formula for the PDF. F theta of x is the normal. That's intentionally hard to read. I don't expect you to memorize the formula, but that's the formula for the PDF of a normal. It's parametric in the sense that I wrote the equation and there are specific parameters, unknown quantities in this model. In the normal case, there's mu and sigma squared. I have a specific probability distribution that I'm assuming, and it can be parameterized in terms of these two parameters. In different cases, you might use a different distribution. It could be binomial if you had success-fail trials. It could be Poisson if you had count data. It could be gamma for right-skewed continuous, could be beta for numbers between 0 and 1. Any of these, if you want to do maximum likelihood, you have to pick one, and then it is a parametric problem because you have specified the analytical form of the PDF, and it therefore has a handful of parameters that are unknown. A non-parametric approach would be able to give us an estimate without any requirements for what the distribution is. For example, the bootstrap. If you wanted like an estimate and say a confidence interval for a parameter theta, and you didn't feel comfortable saying the distribution is such and such, you can apply a resampling technique, a computationally intensive technique, to approximate the sampling distribution. So maximum likelihood is parametric because you have to specify a parametric model, a distribution with a specific analytical form. There are alternatives to doing that, like the bootstrap and others, and they have, you know, some. They're attractive because they enable you to avoid making a distributional assumption. In general, if there is a true distribution, like f theta, and you do maximum likelihood assuming that's the distribution, you will do the best you can. In terms of statistical power, for example, you'll have the most powerful, unbiased inference and everything. If you specify the correct distribution, you'll do the best you can. So you would like to do a parametric analysis in every case if you knew the distribution. But the drawback is if you do parametric inference but you get the distribution wrong, then you don't know what happens. It could be totally wrong. The confidence intervals could be not interpretable as confidence intervals. The p-values could be wrong. So non-parametric approaches are valuable because they work when we don't know the distribution. We can usually beat them by using parametric approaches if we get the distribution right. So we went from confidence regions, simultaneous statements about where a mean vector is, to what we called simultaneous intervals, one per variable. So let me find a specific place to look. One way to do confidence interval construction for every one of your p-variables such that you can then say, I'm 95% confident that all p of them can cover the truth. The way we can do that is to widen the interval. If back here we end up with our nominal coverage to the pth power, that's less than the nominal coverage, that means we need to widen these intervals from what they would otherwise be. And the answer, or an answer, to doing this is that any linear combination of the x bars, like if you wanted to do, let me go to the whiteboard for a second here. Let's suppose we have data that is multivariate normal. So we'll say normal p-dimensional with a mean vector mu, covariance matrix capital sigma. These are IID, independent and identically distributed. Suppose we wanted to make inference. Let's do inference like confidence interval for some linear combination of the mean vector. That looks like a constant a1 times mu1 plus a2 times mu2 p. For example, if we chose a equal to 1, 0, 0, ... 0, we would have A transpose mu equal to just mu 1. Linear combinations of the mu allow us to specify individual means if we want to. I could have an A transpose mu equal to mu 1. I could have A transpose equal to 0, 1, 0, all zeros. That would give me A transpose mu equal mu 2. If I wanted to look at a contrast between one or more of these, what if we said A transpose equals 1, minus 1, 0, 0, 0. This would give us mu 1 minus mu 2. So we're going from a simultaneous confidence statement for the whole mean vector to individual confidence intervals. And what the result we're working around right now says is that we can enable confidence intervals for any linear combination like this. Simultaneous confidence intervals for any linear combination like this. Specifically, I could have a confidence interval right here for mu 1. I could also have a confidence interval for mu 2 and a separate one for their difference. And by constructing them this way, I get to say I'm 95% confident that all three of those cover the truth. The way that we get it is for any linear combination, A transpose mu, we're going to estimate that as A transpose x bar. So here's my estimate of whatever the linear combination of means was. And then I want to do plus or minus a t squared, like critical value, times this thing. Where does this come from? Let me come back here for a moment. We were talking about A transpose mu, which we would estimate as A transpose x bar. And the way that we are going to make this confidence interval is of the form estimate the parameter of interest, estimate plus or minus a scaled, I'm going to call it a estimate with, so we're going to do estimate plus or minus, I'm going to call it a t squared cutoff times the SD of the estimate. That's a general way of constructing a confidence interval. In the context of the maximum likelihood in particular, this is called walled style inference. A confidence interval that's estimate plus or minus some critical value times the SD of the estimate is a walled style confidence interval. There's a corresponding walled style test statistic that does estimate minus what you think the parameter is under the null divided by the SD of the estimate. That's the form of t-tests. T-statistics, tests on proportions, differences in means, they're all this so-called walled style. In our context, we're thinking about an interval for some linear combination of the mu's. What is, the reason I'm writing all this is I'm going to ask, what is the SD of the estimate? We need that. That's what's on the slide. Let's think about that. The variance of A transpose x bar, my estimate. The variance of a constant times a random variable we've seen before, topic 2, I think. This, it can be written as A transpose variance x bar A. And we know what the variance covariance matrix of x bar is, the mean vector. It is 1 over n times s. That's the estimated covariance matrix of x bar. We know expected value of x bar is mu, and we know covariance matrix of x bar is 1 over n sigma. We can estimate that as 1 over n s. So what we have in the context of this confidence interval for a linear combination is estimate plus or minus that t-squared cutoff. I'll go ahead and write it down. P n minus 1 over n minus p. N minus 1 over n minus p. And then I want a critical value from the F distribution with p and n minus p degrees of freedom, the number that puts alpha percent to the right. In the context of a 95% confidence interval, that would be the 95th percentile of this F. So estimate plus or minus t-squared cutoff times the SD of the estimate. And we figured out on the previous line, the variance of the estimate of that is that. So the SD is the square root of that. 1 over n, A transpose S, A. That's what we have right here. That is a way to do simultaneous confidence intervals. And the magic part of this result is that you can make as many confidence intervals as you want. As long as you're doing linear combinations of the means, you can have separate confidence intervals for all the individual variables. You could have separate confidence intervals for every pairwise comparison, as many as you want. The magic of this result is that this holds for all A simultaneously. They will cover with probability 1 minus alpha for all A simultaneously. And that's what we want for simultaneous intervals. Here's a set of intervals about which I am 95% confident. The container data has example code. We saw that the t-squared intervals are like these shadows of the confidence regions. And then I commented that we can actually do better than the t-squared intervals, than those t-squared style simultaneous intervals. In particular, we can get those blue intervals, which also have that simultaneous coverage interpretation. So these are bona fide simultaneous confidence intervals, but the blue intervals are narrower than the red ones. The red ones, because they have to accommodate all linear combinations simultaneously, are as wide as you can get. And they're too wide. If you really want coverage to be 95%, those t-squared intervals will tend to have coverage bigger than 95%. So if you want to get a little more efficient, we can think about trying to narrow the intervals. And a way to do that is with what's called Bonferroni intervals. We don't need to worry much about the detail. I'm just going to point you down here. Here's how you do it. Suppose you have, we have p variables, and suppose we are going to make, we want m confidence statements. This could be m equal to p. If all you wanted was a separate 95% confidence interval for every variable, then you're going to do m equal p confidence statements. But you could also have it be, like I said a moment ago, a separate interval for every component and a separate interval for every pairwise comparison, maybe. In that case, m is more than p. Whatever it is, however many intervals you plan to construct, you write it down first. Then the actual interval, hold on. The actual interval, like here is what you would do for a single one of your components, like variable I. You would do x bar I, estimate, plus or minus a cutoff times the standard deviation of x bar I. And now the cutoff that we use, it looks a lot like what we would do in Stats 101. We would have x bar plus or minus t with n minus 1 degrees of freedom, parentheses alpha over 2 times square root of SII over n. What's different now is that instead of alpha over 2, we did alpha over 2p. If you come to the t distribution, let's say this is t with n minus 1 degrees of freedom. Here would be the t n minus 1.025. For the 95% confidence interval, you would take alpha, 0.05, and divide it by 2, and you'd go find the t value that puts that much to its right. Same thing as the 97.5th percentile of that distribution. But if we're going to make, say, 5 comparisons, suppose we have 5 variate data, and I want separate confidence intervals for every component, then instead of t n minus 1.025, we're going to have to go out further to t n minus 1.05 divided by 2 times 5. That's a smaller number, 0.005. So in order to find the number that puts that much, a bunch less to its right, you have to move further out. This is the cutoff that we would use for the simultaneous intervals. They have been pushed out. The intervals have been widened. And it turns out they have been widened enough that the simultaneous coverage probability for your M confidence intervals is at least 1 minus alpha. It will still be conservative also, just like the t squared, but not as conservative. You have code in the container data for both t squared and Bonferroni intervals. I'll just briefly show you this slide. Critical values. Well, the point of this slide is that the univariate t-based intervals are incorrect. The critical values for a 95% confidence interval, if you're doing univariate t style, these are, like this is the standard normal critical value, which is the limiting result of the t. These are the numbers you would use as the cutoff in the confidence interval calculations if you were just doing univariate style intervals. What follows are a collection of t squared corresponding cutoffs. Notice that they change as a function of p. The bigger the dimensionality, the wider you have to go out, because there's a curse of dimensionality issue that bigger and bigger dimensions makes it harder and harder to account for all the possible uncertainty. And then here's the Bonferroni cutoffs, and the point is if you compare t squared to Bonferroni, the Bonferroni cutoffs tend to be smaller. That means narrower, tighter, more precise intervals by Bonferroni. Very briefly, what we've just seen, all that stuff was under the assumption that we had multivariate normal data. Just like when we do univariate t-tests, we assume that the population is normal, and then we can do a t-test. If we assume multivariate normal, we can do these t-squared tests. Suppose we don't feel comfortable assuming normality. Just like there's a central limit theorem in Stats 101 that enables t-tests with large sample sizes regardless of the population distribution, we have a similar thing here. If the sample size is large, and remember that that has to be with respect to or relative to p. A sample size of 500 is not a big sample size if you have 495 variables. And in this case, with a large sample size, even if the population is not normal, the t-squared statistic is approximately chi-square with p degrees of freedom. So if you have a large sample size, but you make QQ plots and try Box-Cox and stuff, and it never looks normal, your data never looks normal, if you have a large sample size, you don't really have to worry about it.